Hi, I'm I missed that there is an choreography contest today, so I'm late for like 20 minutes or something. So I decided to switch it up and not try to win, but instead try to do the commentary. The color regular is usually much harder than second division, the first round, and usually I'm not able to solve everything, even if I'm really trying. So I hope I will solve at least everything up to E, inclusive with commentary. And well, let's go. Problem A. So we have n people who participate in a race. I guess the race has like two parts, like outward and return. So the outward times are all different, and total times, round trip times, are all different, and we're given that we're given the permutation, basically how they arrive at the finish. The person with fastest return time was awarded the fastest return award. Okay, and they index it in the order of like their outward times. And we asked which of them can have the fastest return time. So for two people, if person A had better outward time but worse full time, it means that than person B, it means that they surely had worse return time, so they cannot be in this set of receivers of fastest return award. So it means that a person can be can possibly be in the fastest return award if like at least they should be better than better in the full time than everyone who was worse than them in the outward time. And I think like that's sufficient condition. Okay. Let's say that for this given person, everyone everyone before them by outward time, like let's say that their outward time is 0, like very small, then our person has like outward time something 1, and everyone after them has outward time like 1 plus epsilon, and then their return time is 0, but like everyone before will have something positive and they can be ordered as we want, and they will still lose to this one. And everyone who was behind, like they can also have some positive return times. It's fine. So since their initial like they're indexed by the outward time, means that the person like is good and should be counted in answer if there is no one before them with worse outward time, so they are maximum on their prefix. So like in this permutation we just count the number of numbers that are maximums on their prefixes, but that doesn't work on this sample, right? 13, then 15, then 20, and that's it. Maybe I need to consider like inverse permutation. The pi is fastest, so for every person their place is given. Well, in such terms it would be like they should be minimum on their suffix. Right? So it will be 17, then 11, 8, 6, 4, 3, 1. That's too much. 8, 6, 4, 3, 1. So that's it. But the limitations are small, so one can use like quadratic solution, but there is a linear time solution. Problem is called insertion sort 2. Permutation, need to sort it, or determine if it is possible to sort it, and I guess print the answer by performing the following operation at most 2000 times, and n is up to 1000, so it's like 2n. So the operation, choose two integers, okay. Okay, so we can take a pair of elements, of consecutive elements, and put them, like insert them back as pair of consecutive elements somewhere. Alright, so that cannot change the parity of the permutation, the parity of the number of inversions. we can always like take so at first we will take 1, and if it is not the last element, then we can take a pair where 1 is the left element and put it in front, and if it is the last element, then we can first take the pair where it is the second element and move it like 1 to the left, and then take a pair when, where it is the first element and then put in front. And we can do that until like if we have at least 3 elements, then we can do that. And if we well, after that we can forget that it exists and continue with 2, 3, and so on. And in the end, the last 2 elements are either in the correct order, so it's fine, or they're in incorrect order, but that means that right now we have 1 inversion, so the parity of inversions is odd, and we cannot sort the permutation at all. So we iterate over the numbers from 1 to n minus 2 inclusive. Then we find the position of that number. We want to put it in the position x minus 1. So if it is already in the position x minus 1, then we are good. If it is in the last position, then we need to move it, take the last 2 elements and move it 1 in front. Now it is not the last. So now we can take elements in positions p and p plus 1 and move them in the correct place, which is x minus 1. And if the end it is incorrect, then the answer is no, otherwise the answer is yes. So here we want to move the pair that is on position P now to position Q, and we know that we will always move to the left. So we need to put it in answer, and I think it should be like P plus 1 and Q. And now we need to actually move it. And we can do it by like moving it to the left one step by one step. So while we have not arrived, p minus minus, and then like rotate the three elements so that the first one becomes the last. The samples are not great, but don't think there is much place to make mistakes there. Alright, problem C. Rooted tree is up to 1000 vertices. X1 is the root. Some vertices have non-negative integers from 0 to n, and some vertices can have no integer in them. Okay, Alice and Bob play a game. Take the operations until all vertices have an integer written on them. Choose one vertex without an integer and write an integer. Amazing game. After the operations, for each vertex v, let f be the smallest non-negative integer not written on any vertex including v in the subtree rooted to vertex v. So for each subtree, we calculate max value. If there is a vertex such that f is equal to k, Alice wins, otherwise Bob wins. And k is just like given initially. So it seems that every time Bob writes something, he should write k in the vertex he writes, because like the given vertex affects only the path to the root, and by writing k we will make all the vertices on path to the root bad. They cannot have max equal to k if there is a number k in their subtree. If Alice can win in just one move, then that's obviously good. It kind of feels like otherwise Alice loses. Like basically Bob's move breaks everything on the vertical path. So let's say Alice writes something in this vertex, but she has not won yet. So like this subtree is not good. maybe there are empty vertices here, but that doesn't matter. Let's choose the vertex without a number that has the lowest LCA with this one. So there is an empty vertex and Bob will move there. So if this LCA is like this, that means that so it is not in this vertex. It means that there are no empty vertices here. But what's important is that when Bob moves in this vertex and just places number k there, that will ruin all the vertical paths to the root. But that means that, well, let's look at vertex A now, right? Like, let's look at some subtrees that have A in it. This subtree is not winning, and all the numbers in this subtree are already set. And it is not winning, otherwise Alice could just win in one move. So, and like subtree like this cannot be winning because we just wrote k here and like it made it bad. So Alice's move is like did not move her closer to winning, because like there is no subtree with this vertex in which she moved that benefits from having this move. None of them can win right now. So that move didn't help Alice. So if Alice cannot move in just one move, then she also cannot win after this move. Like, well, at least in one move, but then like by induction we can prove that Alice cannot win at all. So we just need to check if either there already is subtree with max equal to k, or Alice can create a subtree where max will be k just in one move. We can mark all subtrees that already have number k just in one DFS. Those subtrees are already bad. Now if we have, so we will have like some parts are already bad, but then like there can be other like subtrees that are not bad, and well, we can just okay, I was trying to find like sub-quadratic solution. It is not needed. But it feels like there should be a sub-quadratic solution. Like in quadratic time, it's like you can do basically anything. Like for every subtree, you can like, I don't know, calculate a bit set of all the numbers that we do have, and like IDs of all the vertices that are not set yet, and then for every subtree, like Alice can win using this subtree only if it has a 0 or 1 unset vertex. If it has 0, we just calculate max. If it has 1, we like calculate max, hoping to make it k, and if there is some number that is not used, we can like use it once. Can I do something subquadratic? Well, I can actually have like, I can do exactly that, but storing like kind of bit sets as mergeable segment trees, and this will be n log n. Amazing solution, not gonna write that. Something simpler. Oh, right. I can do just linear, because, well, basically, if I know that there is no k, let's say that everything is filled for now. How can I try to find a subtree with max exactly k? Well, first I mark every subtree that surely has k. That's just one DFS. And now, if like some subtree does not have k but has all the numbers up to k, and its parent is not bad, then its parent is also good, because it still does not have number k, but it obviously has all the numbers that are smaller than k. So we only need to consider like the highest not bad vertex, which parent is bad. And the total sizes, like their subtrees are not intersecting. So I can just iterate over each subtree and it will be linear in total. But now we can have like empty vertices that we need to fill. But if a subtree has more than one, that's also bad. Like I cannot fill all of them. So I can also calculate the number of empty vertices in each subtree, again, just one DFS. And if subtree has more than one empty, then it is also kind of bad. And after that, I will have subtrees with at most one, maximum by inclusion, subtrees with at most one empty vertex and no vertex with number k. So I can only check them, and I can check them in linear time. In time linear, just iterate over the whole subtree, but the subtrees are not intersecting, so it's linear in total. Nice. That is a nice solution. kind of suck if what I said in the beginning is not correct, but I think it is. So in first DFS, we need to mark all the bad vertices. For that, we will calculate like this has k and count of empty vertices in the subtree. If this vertex is empty, then we need to increase into empty by 1. If this vertex has k, then its subtree has k. Okay, now DFS 2, look, if the vertex is bad, we need to like go lower, go to all the suns. Otherwise, we need to check if it is good actually. So if this subtree has k or it has more than one empty vertex, then it is bad. I need to call DFS2 for all the suns, and that's it. Yeah, what I'm thinking about here, like I need to calculate max, and for that I kind of like need the need to clear the Boolean array to mark which numbers I have, and I can do that a lot of times. So that wouldn't be linear, but if I do that only for big enough subtrees, like if there are less than k vertices in the subtree, then max is surely smaller than k. We just don't have enough numbers to cover everything that is smaller than k. So I don't have to do that. But to make this if, I need to pre-calculate sizes, which I can do, but it needs to be done. And if the subtree is too small, then everything that's below is even smaller, and I can just don't bother checking anything. Like I will not be able to get max to be equal exactly k there. Okay, now I do have at least k vertices, so it's fine if I mark if I clear the boolean array in time of k, because like it is smaller than O of size, which is the time I'm already spending, and they will sum up nicely to O of n. So DFS mark, it's just help function that will just mark all the numbers that we have in the subtree. It is not -1, it's mark. And now I will we can sort that not used k, and I will calculate how many numbers we did not have, and if it is at most 1, like if it's 0, then cool, max is k and we have 1. Otherwise, if it is 1 and we have an empty vertex, then we can Alice can move in 1 in the first turn by putting the missing number in that vertex and making the subtree to have max equal to k. So I will just calculate how many are unused, and if it is smaller than the number of empty vertices we have in V, and we know that it is at most 1, otherwise we would do this, then Alice is winning. Can root directed. Given a sequence of non-negative integers d with sum of n-1. That sounds like outward degrees, right? Like there are n-1 edges, and the edges are directed from the root to the leaves, so every vertex except the root has in degree 1, and the root has in degree 0, and the marked with letter D for degree. So like I don't know what will happen next, but I can make a educated guess that I'm like 100% sure is correct, that those are out degrees. Among the n vertex rooted directed trees, a good tree is the one where out degree of vertex I is di. I was correct. Furthermore, for a vertex v of a good tree, f of v, the minimum vertex number of the vertices in the subtree rooted at v. What? Minimum size of the subtree? If f of v is v. That is weird. Find the sum of the numbers of good vertices for all good trees. So we consider all the trees with the given out degrees. For every such tree, we calculate the number of vertices, the minimum vertex number. The vertex number is like v, right? So, okay, f of v is equal to v. It means that this vertex has smaller numbers than everyone in its subtree. Okay. And we are summing over all good trees the number of good vertices. So this is like a double counting problem. So we are summing like over all trees number of good vertices for this tree, which is sum over all trees, sum over all vertices, whether v is good in tree T. And now we can change the order of summation here. So it's for every sum over all vertices or all good trees, where whether v is good in T. And this in terms is like the number of trees in which v is good. So I'm guessing that this will be easier to calculate because like well, the property to be good in tree, it's kind of self-contained in a sense. So we have like vertex v, and we want its subtree to only use vertices with larger IDs, something like that. We should probably go either left to right or right to left and try to insert something somewhere. Oh, I guess it probably shouldn't matter which direction to go. Let's say we're going left to right with numbers. So first we add the root, and it should have like some outgoing degree which is given to us. Then we add the second vertex. It can be put like as a direct sum of the first vertex, and then it will have its own out degree. Or it can be put aside and then it will. No, that's bad. It it will be hard for me to make sure that it is a tree, that I don't create directed cycles. How to just calculate the number of good trees? That's basically this thing for the root. The root is always good because it's always have the vertex 1 is always the root. Maybe some kind of prefer code for directed trees. Probably mean like taking the leaf with the smallest ID and writing down its parent, then deleting it. I will get a list of n-1 integers. The last of them is surely 1, because only the root will be left. And every vertex should be mentioned exactly di times. And by this prefer code, I can restore the tree. Okay, great. So the number of just good trees is the multinomial coefficient, because it's the number of prefer codes, and that's like any permutation of the given numbers. Like, you know, that 1 is the last one, and they have n-2 numbers. Every number has a given frequency, which sum up to n-2. And yeah, get multinomial coefficient. Okay, now how can I make sure that given vertex is good? How to only iterate over trees in which this vertex is good? What if I fix which vertices will be in its subtree? I can only use vertices that has larger indices, and they have some some condition on the degrees, like the total out degree should be the number of chosen vertices minus 1. And like that one shouldn't be like either it is leaf and I just choose nothing, or it should not be the leaf. Okay, and if I fix that, then the number of ways to make a rooted subtree there is just like the same as solving, just counting the number of good trees. So it will be like the product, the number of ways to make the subtree is multinomial coefficient, and the number of ways to make everything else is also multinomial coefficient. And so like the factorials by which I will be dividing are more or less the same. So the only thing that is different is that instead of having n minus 2 factorial in the numerator, it will be split into two parts. And the split depends on the number of vertices in the subtree, which I have to store anyways. So okay, I'm doing dp from right to left. I'm storing like where am I staying now, how like I'm just choosing the subset of vertices that will go into this like subtree of good vertex that I haven't chosen yet, but I will when I reach it. And I need to store like the sum of their di's of the chosen vertices and the number of chosen vertices. That's n cube. That should work. Okay, I understand that was probably incomprehensible. Well, tough teaches. Okay, so I'm going right to left. I will so I'll have the number of chosen vertices and sum of their d values, summing up in like, I guess I just need like the number of ways to achieve that. That's it. Okay, so first, let's consider trying this vertex to be the special snowflake. Iterate or it can be a leaf or it can be not a leaf. If it is a leaf, then well, it is a leaf, so there is no one else in its subtree, and that means that I just should add the number of good trees to the answer, and I will divide by all the factorials of degrees in the end. So now I will just add factorial of n minus 2 that is in the numerator. Otherwise, I'm iterating over how many vertices there will be in my subtree, and actually I need to start from d of v, because at least that many should be in my subtree. Like I have that many sums. So the dp value I'm looking for is k and k minus d of v, because the sum of their d of v, not including mine, should be including mine, it should be k plus 1, which is the number of vertices including me, minus 1, just because like the tree has number of vertices minus 1 edges, so it's k. My out degree is d of v, so the total out degree of vertices excluding mine should be k minus d of v. Okay, now when I calculate the number of ways to make this subtree, I will divide by all the same factorials except for my vertex v. But like that except only if okay, let's just put it here, like if we are talking about the root, then just add the number of good trees. So here I'm not in the root of whole tree because it's a bit different. Alright, so in the end I will divide by factorial of my d, but actually I should divide by factorial of d minus 1. So I need to divide by it now, but multiply by the factorial I will divide later. And also now we have two numerators. Here I have like k plus 1 vertices in the tree, so I should multiply by factorial of z minus 2, which is minus 1. And I should multiply by a factorial of the number of vertices that will be outside minus 2. The number of vertices that will be outside, that the vertices that are not inside. So like n minus k minus 2. So inside, strictly inside, I have k. My vertex still will be in that like outer tree kind of. Yeah, but there is a problem that this can be minus 1. Like this dp should be 0 in that case, probably. But let's just say that this should be non-negative. And add the answer. Okay, now I have to recalculate dp. If I'm not taking my vertex, then nothing changes and those dp values are already calculated. Otherwise, I can take me, so the size will increase by 1 and s will increase by my dv. And now dividing by all the factorials of d and factorial of d of root minus 1. And that should be the answer. Will be amazing if it works somehow. I just love it, Coder. That's probably better problems than anything I solved in Cut Forces in a long time. Problem E. Sequence of n integers from 1 to n. Find the number of sequences of lengths n of numbers from 1 to n. Satisfy the following conditions. The number of occurrences of I in B is at most AI, and number of occurrences of BI in B is also at most AI. What? Strange constraints. Yeah, they are. What are people solving? Everything. But yeah, this problem is solved fast. I can sort A, right? Like most. Well, like I can choose the numbers in the decreasing order of the number of occurrences. So yeah, let's say that I iterate over the number of occurrences from top to bottom, like from n to 0, and I'm maintaining something, probably like how many numbers I have already used and how many positions I have already used. And let's say that I'm now like at d occurrences. And I have already put all the numbers that have strictly more than d occurrences. Then what do we have? Like the number I can choose for this should choose number I. For it, AI should be at least d. Otherwise, number I cannot have d occurrences. It should have less than that. But also, the d positions I'm choosing, they also should all be like a of pj at least d, because otherwise like this number I will be on a position such that corresponding a is smaller than d, but I know that I will put exactly d occurrences of that number, and that's bad. And if I do that, it's all good. Okay. So then, what do I need to store? I need to store numbers used and positions used. And like I kind of it would be ideal to store just like the mask, which numbers I have used and which positions I have used, but it is actually not needed. I'm okay just storing their count. Why is that? And that is because both numbers and positions become available with time. Like if a number is available now, it will be available later until I use it. And the same with position, like because I'm decreasing d, right? Like positions gradually become available, and numbers I also gradually become available. They cannot become unavailable, and so like every number that is used and every position that is used, they were available at the moment I used them, and so they would be available now if they weren't used. That means that right now I can calculate the number of available numbers and available positions, because it's just like how many numbers should be available minus how many numbers I used, and the same with positions. And like how many availables only depends on d and input, and how many I used I store in the DP state. Here I should iterate over the actually like for how many numbers there will be exactly the occurrences. Then I multiply by binomial coefficient. Like I need to actually choose those numbers, and then for every that number I need to choose exactly the positions available without intersections. So that's also like some product of binomial coefficients that is easily calculated. And it may seem that it is like I iterate over d, I have n square states, and then I iterate over number of numbers for this d. So it's n to the fourth, but it is actually not. Why is that? Because I'm iterating over d, and when I'm at some number d, the bound for the numbers used is n divided by d, because I had to for every number used I had to give them like more than d positions. So if there are more than n over d of them, I used more than n positions. That's impossible. Positions used are n. And the same is true for how many numbers I can use right now. Like they're also bounded by n divided by d. Actually, like the sum of this and this is bounded by n divided by d, but that's not really important. So we will have like n cubed times 1 over d squared, and this sum is bounded, so it is of n cubed. And like this constant is small, it's like p squared over 6 and actually divided by 2, so it should be fine. 3 seconds, I find it like I'm sure it is like faster than 0.1 seconds, maybe like 0.2. Yep. So what I need from the array that is given is only like when the corresponding numbers and positions, which are actually the same, become available. So I will only make this and like push them backwards, and then in A of D will be stored like how many numbers and positions should be available if I don't choose anything before that. So B will be this bound on what is the maximum number of numbers that I could have used. I will need to maintain the product of binomial coefficients, so I guess I will iterate over like the starting number of numbers. I need to iterate in decreasing order because I want to reuse the same DP table. So the number of positions that I used, just iterating, and it can be at most like A of D plus 1 actually. So number of positions I have now is A of D minus S that were already used, and I will iterate over how many groups of exactly D numbers I'm using. To use a group of numbers, I need at least D free positions. And so when I do use it, I multiply my current value by choose D positions on P positions and decrease P by D. Now, so the state that I'm going to is I now have used X plus G numbers and I have used like S plus D times G positions. They need to add v here, but multiplied by the number of ways to choose the numbers that I will use. I had a of d minus x options, and I need to choose g of them. This could be negative, but it shouldn't be, because if x is so big, then I couldn't reach that state before, so the corresponding p-value should be 0. So this shouldn't happen. And I think that's it. And the answer is I had to use all the positions, but I can use like any number of numbers for that. Less than 0.1 second. And I guess I have enough time to read problem F. Given two positive integers and m up to 400, we're looking at matrices n by m with zeros and ones as elements. There are 2 to the power of nm of them. Find the number of ones that satisfies the following condition. Quadrangle inequality, but with multiplications instead of additions. Interesting. So basically this says like either both of these are ones, or at least one of this is 0. Like it shouldn't be possible to have 1 1, but some zeros in different corners. So if I have like 1 1 like that, I must have 1 1 like that. The other way around. If I have 1 1 like that, it doesn't matter. So if I have 1 somewhere and 0 here, it means that I cannot have 1 anywhere here. And the symmetric thing is also true. If I have some 1 and I have 0, then all the way down I must have zeros. Otherwise I will have this 1 1 on diagonal but 0. And that's like necessarily insufficient. Okay, let's say I'm looking at my first row. It can be all zeros, that's fine. Or it can have 1 somewhere. Like the first one, the leftmost one. Then it can be all 1s, which is fine. Or it can have some zeros, but then like everything here is zeros. And that is also fine. But all others are like 1s. And after that I know that I can just ignore these columns. Like they cannot be bad. Like I cannot have like 2 1s on diagonal if one of the columns is like full zeros. But I now know that everything here had 1s, so like some of the columns here only had zeros, then here I had 1s, and if later I will try to put 0 here, I will say that okay, for this 1 and 0, like I cannot have 1 anywhere here, so all of them should also be zeros. And well, this row can be all zeros, which is fine, or it can have the first one, but the first one cannot be like after this one, because if I have 0 here, then I have 0 everywhere. So there will be there will be like first 0 in this group, and then before that I have like 1s, and maybe I have some 1s here. So I can have like 1 0 0 1 0 0, but then like these zeros, they go down. I guess I can like fix the number of columns that are all zeros right away, and then just like multiply by minimal coefficient. And then if no columns and no rows are all zeros, then we should have like these segments of ones that start on the right border, and then both borders like move to the left non-strictly, and we must reach the leftmost border. Mm-hmm. And we have to traverse like every column. So it kind of feels like uh, correct, correct bracket sequences. No, they're not nested there. Mm. Well, that is like some polynomial, but we need a cube, and that is not cube, surely. Like if I just store like what is the number of the row and the borders of the current segment, yeah, I like I can get calculate this dp and to the force something. I have 1.5 minutes left. Oh, it's fine. It was a bit easier, I guess, than usual round, but problem D is amazing. Problem E is, I think. Nice round, nice round. Thanks for watching.